In a steam power plant, the inlet state to the high pressure stage of the steam turbine is 40 bar and 350 degrees Celsius. After expansion, the exit steam of this stage is dry saturated, right? The steam is reheated at constant pressure to 350 degrees Celsius before being expanded in the low pressure stage to 0.7 bar. That means the final turbine stage, second stage turbine process is ended at 0.7 bar, right? So that means at that particular time, the condenser process, the condensation process will begin. Okay, so the first question is, they have also given us some points. Assume 100% isentropic efficiency and some say take enthalpy of saturated liquid water at 0.7 bar as 377 kilojoules per kilowatt. That means we have to consider those data also, right? Okay, so first thing, let's sketch the TS diagram first. You have to be very careful when sketching this, right? So now TS diagram, right? Okay. Okay. So this is the temperature axis, right? So now I'm going to sketch the entropy axis, right? Right. So this S stands for entropy, right? So first I will sketch the saturated curve, right? The saturated curve, right? So now I have sketched the saturated curve. So now let's see how to complete the TS diagram as according to the individual processes within the reheat Rankine cycle. Let's see. Starting from the saturated line, right? Then right. Then now you can clearly see why I am using this kind of a ruler, right? After sketching, I will explain each and every line or the curve, why I sketched like that. Right? This should be up to the same height, right? This should be up to the same height. I will tell you the reason why. Then right. This should go little below the saturated line, right? This is where it is started, right? I think now we have successfully sketched the TS diagram, right? Okay, so now carefully listen, right? You have to be very careful when sketching the TS diagram for the reheat Rankine cycle, right? Reheat Rankine cycle, right? Okay, so now let's see all the individual processes within the reheat Rankine cycle. Now be very careful about the points, right? Point number 1, point number 2, right? Point number 3, point number 4, this one, point number 5 and point number 6, right? Okay, so now be very careful. This 1 to 2 is a straight line. This is straight, right? And then this line, I will not put any number there, so doesn't matter. So let's say position alpha, right? So that would be easy for us to understand. Let's say this point as alpha and let's say this point as beta, right? Doesn't matter, right? So 1 to 2 is a straight line, 2 to alpha also a straight line, alpha to beta also a straight line, but be very careful, beta to 3 is not a straight line, that is a curve, right? Because beta to 3 is constant pressure heating, right, above the saturated region, right? Because this dark line represents the saturated curve, right? So again 3 to 4 is a straight line because 3 to 4 is isentropic expansion of the first turbine, right? Then again 4 to 5 is a curve, right? Because that is also constant pressure heating. Then 5 to 6 is also a straight line because that is isentropic expansion of the second turbine. Second turbine is the low pressure turbine, right? Okay, so now I hope all the points are clear, right? So now you have to be very careful when sketching this. Now definitely, as over this problem, you can see this 0.6, right? So this 0.6 represents the exit of the second stage turbine. 0.6 is the final state, exit of the second turbine, right? So that 0.6 is below the saturated curve. Now this curve is the saturated curve, right? This curve is saturated curve, right? So definitely 0.6 is below the saturated curve, right? This point beta is on the saturated curve. This 0.4 is also on the saturated curve because the reason in the problem it is very clearly said that the expansion of the first turbine, right, the final state after the expansion of the first turbine is dry saturated. Look the problem. Now see, after expansion the exit steam of this stage is dry saturated. So this stage means the first turbine stage, right? Okay, so that is also clear, right? And this point alpha definitely on the saturated curve, and point 2 is not on the saturated curve, right? That is somewhere away like this, right? You can clearly see, right? This curve is the saturated curve, right? I think now you have a very clear idea about the points, right? Okay, so now I will sketch the circuit of the reheat Rankine cycle. This is the boiler, right? This is the boiler, okay? That's the boiler. So after the boiler, right, after boiler we have the boiler output, right? So this boiler output is given to the first turbine, right? So it is given to the first turbine. Actually this first turbine is high pressure turbine. This is a high pressure turbine. Because what is the reason? Because this is operating at high pressure, okay, right? So now after this turbine process we have the ending of that, right? After that turbine process we have the exit outlet. So now this outlet is again reheated, right? That is again reheated. That reheat is also within the boiler, right? right? So this is reheated. So I will just sketch a coil like this. So again it is reheated, and it is reheated and it is given to another turbine. Okay, it is given to another turbine. Actually, according to the problem, both the turbines are connected through the same shaft, right? So doesn't matter for your easiness, right? I will sketch a different turbine like this, then it will be easy for you to understand, right? So this is another turbine, right? Another turbine, second turbine, right? And also you can say low pressure turbine, right? Low pressure turbine. So why this is low pressure turbine? Because this is operating at low pressure, right? It is reheated and it is given to another turbine, the second turbine, right? Okay. So then after this turbine also, right, we have the output. We have the output. So that output, so that is the final output, right? So this is the final output, right? So now this output is connected to the condenser, because now the condensing process will begin, right? Now we have the condenser, right? So this is the condenser, right? The condenser process, right? So after condensing, we will get what? After condensing, what we will get? We get water, right? So after condensing, we get water. So that water we again have to send back to the boiler, right? Again we have to send back to the boiler. So for that we need to use a pump. So we need to use a pump, right? So that pump, to that pump we say that is feed pump, right? Okay. So that is the feed pump, right? So we are going to feed it back to the boiler, right? I think now you got what I mean. So now this circuit you have to match with this TS diagram, right? Because now I explained you all the critical points, the position of the point 1, 2, alpha, beta, 3, 4, 5 and 6, right? Then what is the line 1, 2, then 2 alpha, then alpha, beta. Be very careful, beta 3 and 4, 5 are curves, right? Not straight lines. And definitely this point 6 is below the saturated line, right? So now let's see what is that. Right, okay. Now focus this point 3. This point 3 is the starting point or the input to the first turbine, right? Starting point or input to the first turbine. So point 3 is here. This is point 3, right? It's not clear. Use the black colored one. So that's point 3, right? Okay, so that is point 3. So after this high pressure turbine, we have its exit, right? Outlet. So that is situation 4, right? So this point 4 is corresponding to the situation 4, because the reason, again, if you read that question, it very clearly says, in a steam power plant, the inlet state to the high pressure stage of the steam turbine is 40 bar and 350 degrees Celsius. After expansion, the exit steam of this stage is dry saturated. That means the expansion is processed. The expansion happens till it reaches the saturated state, dry saturated state. So up to here. So this point 4 will never go below the saturated line, right? So after point 4, here we have the reheater, okay? So after point 4 it is reheated. Why reheated? Because we again need to give it back to the second turbine. So what is the inlet to the second turbine? So that is point number 5. So this point number 5 is corresponding to that, right? So after that we have the exit from that, that is point number 6. So point number 6 is the exit. While it is the exit of the second turbine, that is also acting as the inlet to the condenser, right? So after the condenser process, right? After the condenser process, it is not 7. After condenser, we have state 1, right? So state 1 is the input to the feed pump, because after condensing we have saturated water, right? After condensing we have water, saturated water, right? HF line, we have water. So that water we cannot automatically send back to the boiler, so we need a pump for that. So after pumping we have state 2, right? So this point 2 is the corresponding situation according to point 2 over here. So now the most important thing is to find the enthalpy values, right? Okay, so now again consider the question. In a steam power plant, inlet state to the high pressure stage of the steam turbine is 40 bar 350 degrees Celsius. That means by using those data we can find what is the enthalpy at the state 3. We can find what is H3. We can find what is H3, right? Okay, so there are several ways of finding H3, no problem. You can either use steam table, right? So from the steam table you refer superheated steam 350 degrees Celsius 40 bar. So that means it is definitely G line, HG 3094. Superheated steam, so HG 3094 kilojoules per kilogram, right? Or else you can use the HS chart. You can see the HS chart like this, but there is something that you have to consider in the HS chart. In HS chart you have to you cannot get the exact value. You can just project the axis and you can just have kind of an estimation, right? Okay, let's see how to do that. So now this H3 3094 kilojoules per kilogram is also correct, but sometimes in the problem, in the exam, they will ask you to solve this problem by using the HS chart. So if you are getting the value from the steam table, so then it is wrong. Okay, doesn't matter. So now let's see how to get that value from the HS chart. So now in HS chart, you know, we have temperatures. In the HS chart we have temperatures like 300 and 400. 300 degrees Celsius and 400 degrees Celsius. So like that we have temperatures. Okay. So in between this 300 to 400, again there are 5 subdivisions, right? Subdivision number 1, 2, 3, 4 and 5. See, subdivision number 1, 2, 3, 4, 5. That means the range in between two curves is 20 degrees Celsius. That means this is 300 degrees Celsius, 300, so this is 320, 340, 360, 380, then this is 400, right? So now here it is 350 degrees Celsius. So 350 degrees Celsius means you have to predict that. So that is 20, 40. So that is in between in between 340 and 360. So it is somewhere in between here, right? So this is 350, right? 350. And so now you have to consider the pressure lines. Again, get the HS chart. In the HS chart, you have pressures like, you know, 10 bar, 30 bar, 40 bar, like that. You have some lines, right? So those lines are representing the pressure. So let's say this is 40, right? So this is 40 bar line. So now 40 bar line, you have to find the intersection of this 40 bar line with this 350 degrees Celsius dotted curve. So that intersection is here. So this intersection you have to project horizontally to y-axis, right? So from that you can read the enthalpy value. So when I read the enthalpy value like that from the HS chart, so then I got that value as let me tell you, I got that value as 3090, right? So you guys can also check it, right? So like that I got it as 3090 kilojoules per kilogram, right? Okay, so within this problem I will consider 3090 value because I am going to refer HS chart for that, because otherwise if I am not going to refer HS chart, then I have to use steam tables, then dryness fraction, bit complicated. Okay, right. So now somewhere I will write what is my H3 now. So my H3 is 3090 kilojoules per kilogram, right? So now you have to find what is the enthalpy at the final stage of the first turbine. So what is the enthalpy at the end of the first high pressure turbine expansion? So that is H4. So how to find H4? Finding H4 is very easy if you are going to consider the HS chart, right? So this is how to do that. So from this point, I told you there is an intersection point, and below this, if you are going to refer the HS chart, below that you have saturated curve. If you are going to refer the HS chart, below that we have the saturated curve that is sketched in black color in my table. So you know what you have to do? This point you have to project vertically downwards, right? Project this point vertically downwards till it touches this saturated line. So then this vertical line will intersect with this saturated curve, and you can find that intersection point. So that intersection point again project horizontally to y-axis. Again project horizontally to y-axis from the Mollier diagram. So then that enthalpy value I am getting as 2780. Is it correct? 2780. 2780 kilojoules per kilogram. Or if not, also there is a way, right, how to find H4, right? But that is bit complicated, but okay, doesn't matter. For this point I will teach you that how to find H4. Okay, right. So now in this problem I am using only HS chart, but doesn't matter. For your study purpose I will teach you that. Okay, so now this is the way to do that. Okay, so now point 3 and point 4, right? So what is 3 to 4? That is isentropic expansion. So that means the entropy at point 3 and point 4 would be same. Entropy at point 3, entropy at point 4 would be same, but at position S3 we have perfectly we have steam, because it is superheated steam, right? So S3, what is the entropy at 350 degrees Celsius 40 bar, 350 degrees Celsius 40 bar, what is the entropy? 6.584. 6.584. Right, so now I told you, here we have that point, right, which is the intersection of 40 bar line with this 350 degree Celsius temperature curve, right? So I told you, sketch a vertical downwards until it touches this saturated curve, right? So when you are going to sketch a vertical until it touches this saturated curve, right, the nearest pressure line that passes through that intersection, if you are going to consider this intersection, there are several pressure lines. Pressure line 1, right, there are several pressure lines, right, so there are several pressure lines passing across that. So the most nearest pressure line to that intersection is 10 bar, 10, right? So the only way of finding that is from the HS chart. Otherwise, I think in the problem they should give that, right? Otherwise you will never know how to find it, right? So this final expansion ends at 10 bar saturated, 10 bar saturated steam, 10 bar dry saturated steam, right? Because 10 bar line is the most nearest pressure line to this intersection. Okay, right. What is the entropy at the point S3? So entropy at S3 is 6.584, right? Because if you are going because from the table, if you are going to find the entropy at 350 degrees Celsius 40 bar, would be 6.584, right? So then what is the most nearest pressure for this entropy under saturated steam? I am again asking, what is the most nearest pressure of dry saturated steam having this value? So let's check from the chart. If we consider 10 bar steam, right? If we consider 10 bar steam, then it has steam entropy of 6.586. We have 6.586, but 6.586 entropy, which is a G, is corresponding to 10 bar dry saturated steam, right? Right. So 6.584 and 6.586 you can consider as a little bit same, right? Because the difference is 0.002, right? The difference will be 0.002, right? So that would be the difficulty that will come when you are going to use steam tables, right? So if you are going to use the HS chart, then it will be very, very easy, right? Okay, so now H4 also clear, right? Okay, right. So now, as according to the reheat Rankine cycle, when the first expansion is ended at the point 4, it is again reheated, right? So now you know where is the reheater, right? So this point 4 to 5 is a reheating process, right? Reheat, right? Reheat. Okay. So now that reheating begins from this point, right? Because from here you found what is the nearest pressure line. So that means at that particular time we have constant pressure heating at 10 bar. Heating at 10 bar till 350 50 degrees Celsius. So if you are going to use HS chart, right? So now this is the 10 bar line, right? This is a 10 bar line. This is 350 degrees Celsius line. So this is a 10 bar line. So what is this intersection? It's here. That means the intersection of 10 bar 350 degrees Celsius, 10 bar 350 degrees Celsius is if you project this horizontally, right? If you project that horizontally from the HS chart, that value I found as 3160. 3160, right? So what is that? H5. Okay, so that is H5. What is H5? 3160 kilojoules per kilogram, right? 3160 kilojoules per kilogram, right? So now then what is the next, right? So now the intersection of 350 degrees Celsius temperature line with the 10 bar pressure line, that is the point over here, right? So this point is the inlet condition of the second turbine, right? So now when you're going to consider the expansion of the second turbine, right, it occurs until 0.6, because this 0.6 is the final stage or the exit. This 0.6 is the final stage or the exit of the second turbine, right? So how to find that? That is the point that you get when you project this point vertically downwards until it intersects with the 0.7 bar pressure line. Because the reason, in the problem it is clearly said that the final expansion process that happens till 0.7 bar. See, before being expanded in the low pressure stage to 0.7 bar. So that means at 0.7 bar, the final expansion process is going to happen, right? So that means the final expansion is proceeded until 0.7 bar, right? So now you know this point, the intersection of this projected vertical line with this 0.7 bar. So this intersection you can project horizontally to the y-axis over here. Can you see that? Right. This point you can project horizontally to the y-axis of the HS chart. So then you can find that enthalpy. I have already found that is 2590. So this enthalpy value is 2590. Is that so? This is 2590, yes. So H6, the enthalpy at the point 6 H6 is 2590 kilojoules per kilogram, right? So now I hope you got the idea. Okay, so now the next part, right? So now I told you 0.6 is the point where the final expansion stage finishes, right? So at this 0.6, right? So now actually 0.6 is the input to the condenser, right? That is the input to the condenser. As you can remember, this is the condenser. Now this 0.6 is the input to the condenser. So after 0.6, what you have is 0.1. 0.1 is saturated water, right? That is saturated water. Saturated water at what pressure? Right, so that is the most important thing. So now you know the final expansion stage is proceeded until 0.7 bar, right? So that means after the condenser at the position 1, what you have is water at 0.7 bar. That means at this point you have saturated water at 0.7 bar, right? Saturated water at 0.7 bar. But luckily in this problem, saturated liquid enthalpy at 0.7 bar is given. See, saturated liquid water at 0.7 bar, 377. No problem. So H1 is given. What is that? 377 kilojoules per kilogram, right? So now you know point or the state 6 is the input to the condenser. After condenser you have state 1, right? That is the input to the feed pump. State 1 is the input to the feed pump, right? Then from the feed pump it pumps to the boiler. Then that is state number 2. So now what is state 2? State 2 is the inlet condition. That is the inlet condition to the boiler, right? So now you have to find what is the pump work. Pump work is H2 minus H1. That is the pump work, right? So difference in that enthalpy, right? Because you have to use the feed pump to pump it back to the boiler. So that means definitely H2 enthalpy must be higher than H1 enthalpy. So that is when H2 minus H1 is the pump work. So now how to find the pump work? Pump work equals specific volume of saturated water. Specific volume of saturated water at 0.7 bar. Be very careful. Specific volume of saturated water at 0.7 bar. Okay? Right. Multiplied by pressure difference in kilopascals. Pressure difference in kilopascals of the input pressure of the first turbine. What is the input pressure of the first turbine? Okay, so let's say that P3, right? Because 0.3 represents the inlet condition of the first turbine, so let's call that P3, right? P3 is the pressure, the inlet pressure to the first turbine, minus pressure when the final expansion stage, or pressure at the end of the final turbine process. So what is the pressure at the end of the final turbine process? That is P6, right? Okay, right. So now you know 1 bar is 100 kilopascals, right? 1 bar is 100 kilopascals. Specific volume of saturated water at 0.7 bar. Here now I have a steam table, some saturated water property table, right? So I told you in this chart pressures are given in kilopascal. So now what I really want is, I want specific volume of saturated liquid. I want specific volume of saturated liquid at 0.7 bar. 0.7 bar means 70 kilopascals, okay? 0.7 bar means 70 kilopascals. So but in this chart I have specific volume of saturated liquid, which is VF. Now be very careful, it is not VG, okay? VG is the specific volume of saturated steam. This is saturated liquid, so be very careful, because if you are going to refer the chart, it will provide specific volume for both saturated liquid and vapor. So now here I want specific volume of saturated liquid VF at 0.7 bar or 70 kilopascals, but unfortunately in this chart we don't have for 70 kilopascals, but we have specific volume for 75 kilopascals. Specific volume for 75 kilopascals is 0.001 0.001037 meter cubes per kilogram. So that is the specific volume, right? So now we know that. Okay, so now I will continue. So now what is the pump work? Specific volume of saturated liquid at 0.7 bar, that means 70 kilopascals, but unfortunately in that table we don't have 70 kilopascals, we have it for 75 kilopascal. So what is that value? 0.001037. 0.001037, right? Multiplied by what is the inlet pressure of the first turbine? That is 40 bar. 40 bar in kilopascals is 4000, right? 40 bar in kilopascals is 4000 minus what is the final pressure at the end of the second stage turbine expansion? 0.7 bar. 0.7 bar means that is 70 kilopascals, because this pressure difference should be in kilopascals, right? So 4.075, so let's say 4.08 kilojoules per kilogram. So that is the pump work. Now we have to find what is the net work. What does it ask? Net work and thermal efficiency of the cycle. Okay, very easy, right? So what is the net work? So net work equals total turbine work minus pump work, right? So what is the total turbine work? Turbine work from let's say TB, turbine work from first turbine plus turbine work from second turbine minus pump work. Okay, right. What is the turbine work of first turbine, high pressure turbine? H3 minus H4. H3 minus H4. H3 minus H4, right? That is the turbine work of the first turbine. So what is the turbine work of the second turbine? H5 minus H6 plus H5 minus H6 minus this pump work. Okay, so now very simple task. H3 minus H4, substitute there. H5 minus H6, substitute there. Then minus, our pump work is 4.08. I will tell you what is the net work done, right? Difference of this plus difference of this minus pump work, it is 875.92. Check it, 875.92. 875.92 kilojoules per kilogram. That is the net work. So now we have to find the thermal efficiency, neta, or the cycle efficiency. What is the cycle efficiency? That is the ratio of net work and heat input. right, multiplied by 100%, right? Right, so that is the cycle efficiency, right? So now that means now we have to find what is the heat input, right? Right, so now let's find what is the heat input. Very easy. Heat input, right? So now heat input means that is the enthalpy difference in between boiler input and boiler output. Enthalpy difference in boiler output, because output is the highest, boiler output and boiler input. Enthalpy difference in boiler output and boiler input plus, but be very careful, here we have a reheat stage also, right? What stage? We have a reheating stage also, right? Because at the end of the first stage turbine process, we are again going to reheat, okay? Right. So now that means now to there we have to add what is the extra energy required in order to heat from position 4 to position 5, right? So that means we need to find that also. What is the extra energy that we need in order to heat from position 4 to position 5? So that means enthalpy, difference of inlet enthalpy of second turbine, enthalpy difference of inlet enthalpy of second turbine and outlet enthalpy of first turbine, right? You got it? So what is the total heat input? Enthalpy difference in between boiler output and boiler input enthalpy plus enthalpy difference of inlet enthalpy of the second turbine and the outlet enthalpy of the first turbine, because it is heated from the outlet from the first turbine to inlet of the second turbine, right? I wrote that in order to have a clear understanding, right? Right, so that means if I am going to write that, heat input would be what is the inlet of the first turbine or the outlet from the boiler. So now here you have to consider one thing. Boiler output is same as input to the first turbine, okay? Boiler output is same as input to the first turbine as according to the problem, right? Generally there must be some heat loss, right? Because exactly what the boiler produces cannot be the input to the turbine, right? There can be some heat loss, right? But according to this problem, you are going to consider boiler output as the input to the first turbine, right? Okay. So what is, how to find that? Boiler output or turbine, first turbine input H3 minus H2. H3 minus H2 plus enthalpy difference between input to the second turbine H5 minus output of the first turbine H5 minus H4. That's it. H3 minus H2 plus H5 minus H4. H3 you know, H5 you know, H4 also you know, right? Let's calculate. You don't know what is H2. You don't know what is H2, but you know what is H2 minus H1 and you know what is H1. So that means right? Because H2 minus H1 is the pump work, right? Okay. So that means H2 equals pump work plus H1, right? So what is pump work? 4.08. What is H1? Enthalpy of saturated liquid at 0.7 bar, 377. 377. So what is H2? 381.08 kilojoules per kilogram, right? So H2 is 381.08 kilojoules per kilogram. So that is H2. So that means now you know what is H2, right? So what is H3? 3090 minus 381.08, 381.08 plus what is H5? 3160 minus what is H4? 2780. 2780. What is the answer? 3088.92 kilojoules per kilogram. So that is the heat input. Neta will be 875.92 divided by 3088.92. What is that? 875.92 divided by 3088.92. It's a very low value. 28.36%. Because even though I explained that in the video, sometimes you might find difficulties. So I think now the problem calculation will be okay, but doesn't matter. I will teach you about that HS chart thing again, right? I will sketch the HS chart, right? H means this is enthalpy axis, right? Enthalpy axis is in kilojoules per kilogram, right? This is entropy, right? That doesn't matter. S, entropy, right? Okay. So now what is the first thing that you have to do as according to the problem? I told you there are temperature lines. Okay, we have 300 degrees Celsius line, and after that we have 400 degrees Celsius line. Okay, but in between 300 to 400 there are 5 subdivisions where each subdivision, right, is having a range of 20 degrees Celsius. In between 300 and 400 there are 5 subdivisions. If you carefully look the HS chart, there are 5 subdivisions, right? I will sketch 1, 2, okay, 3, 4, 5. See, subdivision 1, 2, 3, 4, 5, right? Okay, so that means we have 320 degrees Celsius temperature curve, then 340, then after that what we have is 360, then 380 and 400, right? Like that. So but as according to this problem, what is the temperature of the first turbine? What is the input condition to the first turbine? That is 350 degrees Celsius. So 350 degrees Celsius is in between 340 and 60. Careful, huh? Right? This is 20, 40, 60. So 350 degrees Celsius line is in between 340 and 360. right? So this line is a kind of an imaginary line that you have to imagine, right? After that, what you have is you have pressure lines. Then you have to find what is 40 bar pressure line, right? Line or curve. Let's say this is the 40 bar pressure line, right? So that is the 40 bar pressure line. So then there is an intersection point of the 40 bar pressure line with this 350 degrees Celsius imaginary temperature curve. That is here. So project this point, project horizontally to this axis. Then you can find that enthalpy. Actually, what is that enthalpy? That enthalpy must be 0.3, means H3. Okay, right. So then, so now you know in the HS chart, if you go a little bit below, you have the saturated steam line or saturated steam curve or the saturated region. Let's say saturated region, right? Because in this problem it is clearly said the first expansion stage is processed until the steam is dry saturated steam, right? Okay, so it is clearly said in the problem, right? The expansion of the first turbine is processed until the saturated line. So from this point, project vertically downwards, right? I will use the ruler, right? I will use the ruler, project vertically downwards until it touches the saturated curve. Then here you have the intersection. So from this intersection, again sketch or again project horizontally to y-axis. Then you have enthalpy 4, right? Okay, got it, right? So now the next scenario, right? At this point onwards, right? So when it reaches this point represents the ending state of the first turbine process, right? So when the first turbine process ends, the state of steam is dry saturated, right? So at this point 4, now this point represents point 4, right? So this point 4 is symbolizing saturated steam at a particular pressure. So what is that particular pressure? So when you are going to consider this point also, there are several pressure lines that are going closer to that. So you have to select what is the nearest pressure line. You have to select what is the nearest pressure line that passes through that point. So that is 10 bar. So that means at the end of the first stage expansion, you have 10 bar dry saturated steam, right? So what is the steam pressure at that scenario? 10 bar, right? Because 10 bar line is the most nearest pressure line. From this point onwards, it is again heated until 350 degrees Celsius, right? It is again heated at the same pressure at the end of the first stage expansion, which is 10 bar. So again, what you have to do? Again, you have to consider this imaginary 350 degrees Celsius line. See, imaginary 350 degrees Celsius, because the reason between 300 to 400, there are 5 subdivisions, right? Where one subdivision is having a range of 20. That means you have after 300 you have 320, 340, after that you have 360. So there is no line for 350. So that is why you have to sketch a imaginary line for 350. It's not a magical thing, simple thing, right? So this imaginary dotted line is that 350 degree Celsius line, right? So you have to find the intersection of this 10 bar pressure line, right? Intersection of this 10 bar pressure line, intersection of the 10 bar pressure line with this 350 degree Celsius temperature line, right? So here there is an intersection. So that intersection point again project horizontally, to this axis, right? That is why I am always using this ruler, project horizontally to this axis. So then you can find that enthalpy. So what is that enthalpy? That must be 3, 4, that must be H5, right? So that is H5. The value of H5 you know, you can refer the video, understand, right? So that is how it happens, H5. So now we are at here, right? So now starting from this point, in this problem it is said the final expansion stage is processed until 0.7 bar. So then you have to extend this line vertically downwards until it passes 0.7 bar pressure line, right? So definitely this 0.7 bar pressure line is below the saturated line. This is the saturated line, okay? This is the saturated line. Definitely this 0.7 bar is below that line, right? So you have to extend this vertically downwards. This point you have to extend vertically downwards until it touches or intersects with 0.7 bar line. So this intersection point you again project horizontally to y-axis. So then what you would be getting? Then you would be getting what is H6. That's it. Okay then, thanks. So now we solved that problem with a very good explanation, right? Thank you so much for your kind participation. Wishing you all the very best for your thermodynamics exam. Thank you.